Welcome back to Street Talk Unplugged. This is your host, Tim Scarf. I have COVID this week, so sorry if my voice is a little bit hoarse. I'm going to do a little bit of housekeeping to start things off. Now, if you want to jump straight into the interview, then check out the table of contents and just skip right ahead. We're doing our first community event on Discord this Wednesday. Andrei Zakharovich is presenting a session on discrete program synthesis, and then we're going to have a Q&A and discussion afterwards. So it's kicking off at about 5 p.m. UK time. Nearly 500 people joined our Discord in the first week or so, which just blew my mind. We already have the beginnings, actually, of a really exciting Discord community taking shape. We've got some amazing people in there, so now's the time to jump in and say hello. At the beginning of the year, we decided to experiment with releasing a couple of audio-only podcasts called Unplugged, where we don't spend much, if any, time preparing beforehand. The main difference between MLST and other podcasts has always been the prodigious amount of preparation that we put in before the shows. And it was strangling our output a little bit, so I guess we just wanted to do the counterfactual, run an experiment and see what would have happened if we didn't suffer from the curse of perfectionism. MLST is a think tank. As you probably noticed by now, we don't just invite a bunch of random people on to monologue or pitch their startup. We get straight into the weeds and we have a deep technical discussion with our guests. Perhaps the main difference with the Unplugged shows has been that the dialogue has been a little bit more open-ended and accessible. We did change the plan a little bit though, as you probably noticed. We decided to publish these Unplugged shows on YouTube as well. So the video from the interview has gone up there. I think some of you are really passionate about YouTube being your primary delivery platform. And I personally have always been a huge fan of YouTube myself. I think it just adds so much value, being able to see the facial expressions and the visual cues. To be honest, I've been really surprised at how flowy and natural these conversations have been. And according to the analytics, the engagement on the conversational segments has been higher on these shows than our traditional ones. So maybe it's just due to their informal, kind of open-ended and accessible nature. I'm not sure. But we have had a lot of feedback that our content is quite hard to understand and quite academic in nature. And, the detailed preparation we did probably only served to make the shows more opaque to people. We do pride ourselves on being really technical. MLST is almost certainly the most technical podcast on ML, but there's a sweet spot to be found somewhere. As you probably noticed, we do try and zoom out and we focus on some deep ideas and themes, which come up over many shows. So a big one is the dichotomy between discrete and continuous, for example. Now, the show right here, this one, was actually the very first Unplugged show which we filmed at the beginning of January. Listening back to it now, it's probably my favourite one. There is actually one other one which is amazing, which hopefully we can get approval to release. There's a bit of a backstory there, but this one's really, really good. And I think it's because of the incredible rapport and friendship we had with Walid Saba. We delayed the release of it because we mentioned Bengio in the introduction and we didn't want to spook him off. He accepted our invitation back in January to come on the show, but I'll explain more about that in a minute. But yeah, to finish the thread on Unplugged, this is an experiment. We probably will run it until April, and then we're going to pivot and we're going to make some pedagogical content, kind of 3 blue, 1 brown style content without any invited guests, and we'll see how that performs. But so far, Unplugged has been pretty successful, I would say. Now, trigger warning. This episode is very critical of deep learning. Walid Saba is probably the, if you think Gary Marcus is a critic of deep learning, Walid Saba is one notch up. If you're not up for that, just skip this episode, right? We really want to capture diverse opinions in the AI landscape, and I'm not just saying that. Look on our front page, right? We've just interviewed 2 of the 3 godfathers of deep learning in the past 5 videos or so. Personally speaking, my salary does not depend on a subscription to any particular viewpoint in AI, which is perhaps the main reason we have the freedom to explore. I really love diversity of thought in general, and that's why you'll see us making content on loads of ideas, some of which I don't even subscribe to, like AI alignment. We're planning a big show on that now that my mate Connor Leahy has, found his way to London. It's really important to hear opinions from people outside of our circles, even if we don't want to hear them or we don't like the people espousing them. Unfortunately, because of the tribalism in our community, many folks have refused our invitations to come on MLST. And a couple even told me straight to my face it was because we had Pedro Domingos on the show and they didn't want to be tarred by association. It might also have been because Yannick has been quite outspoken on AI risk and identity politics and ethics, but this is the really annoying thing about podcaster Stan, right? It's really hard to get genuinely diverse views on the same platform. This is why so many podcasts become more polarized on the one hand or just completely bland on the other. Even some of the podcasters I really love, like Sam Harris, they've just become really entrenched in recent years, right? Sam doesn't invite anyone on that he doesn't agree with anymore. We've had and by the way, Sam's an interesting case. I mean, I don't really agree. I don't really agree with really much of anything he says, but I just love listening to him for some reason. He's got such a soothing voice. But anyway, as I said, he doesn't invite anyone on that he doesn't agree with anymore. We've had a couple of comments saying that we've invited too many well-educated white guys on the show. Well, to be honest, most of the diverse folks just ignore our invitations. I can assure you we've actually invited most of the diverse big names in ML. I don't feel it's appropriate to say their names, but you can probably guess who they are. We are inviting more. I'm extremely open-minded, right? And I hope that we can have more diverse guests and topics in the future. I don't want to mislead you. I'm actually dead against cancel culture and identity politics, but it's not a hill that I want to die on. Keith and Yannick would die on it all day long, but I would rather appease people and attract interesting guests on my podcast rather than alienate them over an ideological point of principle. I didn't even want to use the term cancel culture in the introduction because it means you'll instantly put me in a political box, right? I genuinely think that sunlight is the best disinfectant for bad ideas. But I also think that there are very few issues which you should be genuinely cancelled for. Inciting or committing acts of violence seems like an obvious red line to me, but it's not clear where the boundary should lie. The situation in Ukraine has really put a lot of things in perspective for me in the last week or so. Now, I know Pedro got himself into a lot of trouble on Twitter recently over comments he made about women and positive discrimination in the workplace. He was making some inferences about a study, and many highly respected academics argued that he made an incorrect inference based on the study. Now, I didn't even read the study, but based on the uniform denunciation of Pedro's comments, I assume he got it wrong this time. But here's the thing. If I actually believed that Pedro was a misogynist or a racist, I wouldn't have invited him on MLST. Just because I don't believe in cancel culture in principle doesn't mean that I wouldn't invite him on MLST regardless, right? What's really going on here is that there's a bunch of people who hate Pedro's political views, and they're trying to censor him by deliberately mischaracterizing his views. Anyway, how did we get here? Yes, so we were talking about deep learning bashing, which is only slightly less ideological than identity politics, by the way. Deep learning is a revolutionary and fascinating technology, but it's also got some glaring pitfalls that even the best in the field don't want to acknowledge because their careers depend on maintaining the illusion for as long as possible. The immediate future will probably be a hybrid of neural networks and symbolic approaches, and it'll probably be here faster than you realize. Dr. Walid Saba is an old-school polymath. He has a background in cognitive psychology, linguistics, philosophy, computer science, and logic. He's now a senior scientist at Sorcero. Now, Walid is perhaps the most outspoken critic of BERTOLOGY, which is to say, trying to solve the problem of natural language understanding with the application of large statistical language models. Walid thinks that this approach is cursed to failure because it's analogous to memorizing infinity with a large hash table. Actually, Walid thinks that the various appeals to infinity by some deep learning researchers are risible. Now, it's not hyperbolic to say that MLPs are like locality-sensitive hashing tables. I mean, that's precisely what Dr. Randall Balistrario from Meta AI Research demonstrated in his Spline Theory of Neural Networks paper. Yazaman Rezegui from UC Irvine recently published work apparently indicating that this is indeed the case in large language models like GPT-J, with respect to their ability to multiply numbers together zero-shot. She demonstrated that their performance was linearly correlated with the term frequency in the training corpus, strongly indicating that the models had just memorized the answer. Well, it turns out that we're going to be interviewing Yazaman and also her PhD supervisor, Samir Singh, in the next couple of weeks, so keep an eye out for that. Walid has made a name for himself, railing against the apparent lack of any understanding in the latest state-of-the-art statistical language models, and also what he perceives to be hyperbole and intransigence in the deep learning community. Now, there was a paper recently released called The Defeat of the Winograd Schema Challenge by Vid Kosygin. and also with some of the usual suspects like Gary Marcus and Ernest Davis et al., talking about the perils of metric optimization and NLP using the Winograd Schema Challenge. Now, the Winograd Schema Challenge was designed to be a good proxy for common sense reasoning. They were first proposed by Hector Levesque in 2011, and by about 2019, a number of these transformers models were getting better than 90% accuracy on some of these problems. Now, an example of a Winograd schema is as follows. The woman stopped taking the pills because they were pregnant or carcinogenic. Now, does the pronoun they refer to the pills or the women? Well, it changes depending on the final word being pregnant or carcinogenic. Kosijan et al. Pointed out that the naturalness of the Winograd schema task is particularly striking as compared to many other natural language tasks, such as benchmarks, right? It makes it seem compelling as a powerful test of human understanding. And this stands in stark contrast with the other tasks, such as considering the entailment between two sentences, or identifying segments of a text which answers a question, or maybe word analogies, or even predicting the next word in a sequence of words, which is the task in traditional language modeling. Now, Walid thinks that the biggest problem that we need to solve in NLP is the so-called missing information problem, which is that we don't say everything that we mean. We need to reason and extrapolate to fill in the missing blanks, and neural networks only extrapolate when given explicit handcrafted priors for a particular invariance, or hybrid architectures which effectively generate additional training data to fill in those blanks. Walid recently released an article titled "AI Cannot Ignore Symbolic Logic, and Here's Why." The article was even reposted by Professor Yann LeCun and Professor Yoshua Bengio, two of the godfathers of deep learning that we've just recently had on. Now, Yann made it abundantly clear that he disagreed with the article almost 100%, and Walid led with a quote from Yoshua Bengio. Yoshua once said that deep learning, as it is now, has made huge progress in perception, but it hasn't yet delivered on systems which can discover high-level representations, the kind of concepts that we use in language. Humans are able to use these high-level concepts to generalize in powerful ways, and that's something that even babies can do, but machine learning is very bad at. End quote. Now, that, of course, was music to Walid's ears, right? Walid is a traditional symbolist. He thinks that without symbolic and logical reasoning, we'll never build something which even partially resembles artificial intelligence. Bengio has actually been much more open to discussing the limitations of deep learning, as opposed to Hinton, for example, who recently said that very soon deep learning will be able to do anything. Now, Bengio responded on LinkedIn saying that he thought that there was a misunderstanding in Walid's post, arising from the sincere but incorrect belief that it's not possible for neural networks to do symbolic manipulation, although unfortunately he didn't explain how exactly he thought they could. He agreed with Walid on the importance of symbolic manipulation and asserted that, indeed, the human brain must be doing it somehow, and that he thought it would be essential for improving the state of the art in AI, primarily because of its importance in abstraction, or abstract extrapolation. Now, we demonstrated comprehensively on our LeCun show that MLPs can be thought of as locality-sensitive hashing tables. Now, let's not forget that all neural network architectures have an MLP backend. Neural networks decompose an input space into an exponentially large number of nested polyhedra, which represent volumes of statistical generalization around the training data. They are storage buckets. They're not computational devices, right? So saying that neural networks can perform symbolic manipulation, to me, is roughly equivalent to the statement that locality-sensitive hashing tables can perform symbolic manipulation. The most simple way to understand this is that the representational capacity of a neural network is fixed. But if you take the symbolic quantity x equals y squared, it's an infinite table, right? If you watched our episode on geometric deep learning, you would know that all of the deep learning architectures get around this problem by constructing inductive priors, which basically replicate information in respect of an invariance. So for example, translational symmetries in CNNs. What they do is they kind of replicate this information into those buckets of the hash table on the MLP backend during inference or training. Now, Bengio said that he thought a particular kind of deep learning architecture with an appropriate system to inductive bias would give us what's needed. And it's the core of his research program, actually. Most importantly, he doesn't think that the solution will be a simple hybrid of symbolic methods and neural networks where we just glue them together with some high-level interface. Now, Bengio thinks that the main reason this won't work is because you need to have end-to-end learning, and that you need to have some kind of system 2 for reasoning and planning. Now, this is where it gets really interesting. Now, I'm quoting directly now. In order to scale system 2 forms of reasoning and planning, we need to have a powerful but implicit form of search that system 1 neural networks can provide, like in AlphaGo, for example. What I like to call the imagination machine, which spontaneously pops up reasonably good solutions, paths, reasonings, and explanations in our conscious mind without the need for explicit search. End quote. Now, Bengio is of course talking about GFlow nets, and you can watch the show we did on GFlow nets, and indeed the interview that we conducted with him. It was really, really cool. But to contextualize this a little bit though, all neural networks have an MLP backend, which is a locality-sensitive hashing table. The only reason these models can extrapolate is if we create an inductive prior to pack all of the information into those buckets of this hash table. The complexity here depends on how structured and how large the functional space is. Walid Saba argues that language is not amenable to any statistical modeling methods because it's infinitely large, discrete, and unstructured from a statistical point of view. Now, coming back to Walid's article, he says that the problem deep learning aficionados have in admitting symbolic and logical reasoning is that all of this will make neural networks just one of the tools which can be used at low-level tasks such as perception and pattern recognition, while symbolic and logical reasoning will have the supremacy of modeling human-like high-level reasoning. Now, and by that I mean the kind that we use in complex problem-solving tasks and language understanding. Now, for example, Walid says that there are many high-level templates which underlie most of how we function in the world, templates which are universally valid across cultures and ages and individual experiences. Walid argues that the universality and application of these templates on concepts of specific types precludes learning them bottom-up from data because, one, we cannot and we're not allowed to learn them differently, and two, that there's just no time for a child to learn all of these common sense naive physics templates bottom up, although their behavior by the age of 3 clearly shows that they've mastered all of these templates. If you say to a 5-year-old kid that his toy is in the bag and the bag is now in his room, the child will know that his toy is now in the room. Try telling the 5-year-old kid that the toy is still here. It's not like this Daniel Kahneman view of the world where we allow significant irrationality. When you look at our low-level conception of reality, there's no surprise. There are no deviations. Think of transitivity. If you ask your child to put the camera in a briefcase and it didn't fit because the briefcase was too small, try telling the child to put the camera in a smaller briefcase. Walid actually told us that he did this experiment with his kids. Walid asserts that everyone acquires exactly the same abstract categories or templates. It's like they're a gift to us from physical reality itself. They are primitive, abstract categories of our physical reality, and they evolved into our DNA. Now, I did challenge Walid on whether the progressive acquisition of these abstract templates into our DNA could itself be akin to a learning process rather than the binary acquisition which he describes. And that did leave him a little bit lost for words. But Walid eschews any kind of learning. He thinks that there is a Platonic configuration of templates given to us from reality, and we can only discover them. His main objection to them being learned is that they cannot be learned differently, and thus they cannot be the result of our own individual experiences. He thinks that they are laws of nature which were implanted into our DNA, that, we need them to be able to function properly. Walid does not like the notion that knowledge can be learned progressively or that it can be learned differently. It's very much a binary thing to him. Walid gave me the example of a toy going out of sight of a 4-year-old. They would know that it did not disappear, but it must be somewhere else, right? Because they know that some physical objects must be located somewhere. The logic here is even more sophisticated and operates on objects in a typed ontology. So while the toy must be somewhere, if it was not completely destroyed, well, actually, this isn't true of all physical objects, right? I mean, for example, if the object that went out of sight was an apple, we might hesitate to conclude that it, must be somewhere else because the apple might have been eaten. So we have this very sophisticated logic that symbolically quantifies over objects of a certain type, each with its exceptions and rules. All of this is going on in the head of a child. Incidentally, these high-level templates are mostly employed using neither induction nor deduction, but abduction, right? Which is to say, inference to the best explanation, which is, for the most part, ignored in artificial intelligence research today. Walid says that when confronted with a new situation, the relevant template is instantiated, right, or filled out with specific objects of the appropriate type in a way which is consistent with the overall logic of the template, right, for the best explanation of where the toy is, given that the bag containing the toy was moved to the bedroom and absent any exceptions, is that the toy must now be in the room. If there are no common sense templates which have a logic consistent with our physical world, how does a child learn all of that bottom up from data by the age of 2 or 3? Walid thinks that all of the replies from empiricists and bottom-up theorists to these questions end up being no more than hand-waving, and the best example of how autonomous driving technology, where these high-level naive physics templates are essential, failed when it ignored this part of our cognitive apparatus. All of this, which allows us to behave properly according to the logic of the world we live in, also applies to language. In his article, he gives many examples, right? So one of them is the loves template. Walid is showing how these high-level symbolic templates can blow up exponentially with instantiations of instances that are of the appropriate type. Let's look at a couple of examples. My cousin loves playing the guitar, where the entity here is an activity. My sister loves glamour, where the entity is a quality. My neighbour loves Grandma Sue, where the entity is a person. The boy that comes here every morning wearing a red cap loves AC/DC, and the entity there is a social group. You can probably see where this is going. When you have the abstract templates, you can extrapolate into an infinite number of possible situations in experience space. Walid thinks that we are born with these templates baked in, and that we become aware of them, or they come to life, when we first see instantiations of them. Walid concludes his article by saying that none of these observations are new. Most of this was already observed and known and argued for, even proven, since the early 1980s, and he suggests reading the philosopher Jerry Fodor, perhaps starting with Concepts, where cognitive science went wrong, and having another good look at the cognitive science literature with an open mind as an antidote to the current deep learning malaise. So anyway, now I give you Dr. Walid Saba.
So Wally, you brought up this problem that I thought was kind of interesting, and it goes like this. Consider the following 2 sentences. A, the trophy did not fit in the suitcase because it was too small. And B, the trophy did not fit in the suitcase because it was too big. Now, we as human beings, we know where to assign small and big, whether it should belong to the trophy or the suitcase, but we do that because we have this kind of extra context. So, for example, I know that typically things go inside suitcases, like trophies, not the other way around. And I also know that in order for something to spatially fit into something, it has to be smaller than the other thing. So there's a spatial relationship, right, that I'm aware of, this kind of context. And I think you made the point that, look, if you just look at statistically something like a neural network transformer, it's going to find that small and big are virtually statistically identical, and that it's going to fail to do this type of reasoning that we can do as people. But my question is, it seems to me like that knowledge about, how things fit into another thing, or that typically things go inside suitcases, I could glean statistical knowledge about that from the corpus. Couldn't I? I mean, where does that kind of go wrong that context could still be learned statistically?
Okay. First, the argument, someone might argue, and I know someone like Tim has hinted at that argument, that small and big, although just word embedding kind of similarity, they might be very close. In the wider context, there are techniques where you can take their position into consideration and their contribution to the overall meaning would be significant, although statistically both are as likely in the same context. Yes, you can increase your statistical significance between them slightly, and I underline slightly. So from them being almost identical, they become, in a wider context with attention and transformers, they become slightly distinguishable, not much. But that, having said that, we can get into the technicalities of that. That is not the main problem here, actually. It's not only because small and big are statistically similar. The problem is much bigger than that. And here's what the problem is. Again, it goes back to infinity. Learning from instances is theoretically plausible if I can live 200 billion years. So here's the problem. The trophy can be replaced by the laptop, by the ball, by my camera. The camera did not fit in, and the suitcase can be replaced by the closet, by the drawer, by the trunk, anything that I can put stuff in.
Yeah.
So this is a template, and you can change did not with did, and you can change although by because, and because by since. So the combinations, I can give you, in 1 second, I can give you a reasonable argument that says this sentence is a template for 200 million sentences.
Yeah, but the thing is, this is obvious to us because we've been speaking about the curse of dimensionality. And that is all about how when you have increasing dimensions and statistics, the volume of the space increases exponentially, which means actually you have a specificity, but you have no approximation boundary, right? So you lose generalization. It's exactly the same here. So, you were talking about the difference between big and small. That's the wrong way to think about it. Actually, we have specificity. We have too much specificity. We actually have an exponentially large number of templates, but we'll never have statistical significance on any representation of those templates because it's in a vast space.
Well, and every template has a combinatorial number of instantiations of it.
So it's the curse of templates rather than the curse of dimensionality.
I was going to say it's not dimensionality. It's the what is it called technically? Productivity as in production rules.
Production in a logical sense, like production
in
rules.
a logical sense, or in a formal automata sense. The productivity of even a simple template like the one I just described, and this is a simple sentence, guys. The productivity is, I can show you the numbers. We're talking about 200 million sentences a child can make from this template alone. So yes, you can learn it from observation, but how many things I have to see not fit in things? Remember, I'm talking about learning from actual instances. Like otherwise we're doing hand waving. People say, "Oh, but then I can put this bias in." No. Learning from instances is brutal, guys. So when you want to defend it, you have to tell me how. Hold on. You have to tell me, look, learning from data, either you adopt it and defend it or you don't. There's no middle, right? If you want to defend learning from observations, a template like this, you have to convince me how a child learns 200 million sentences from few examples. If you don't have an explanation for that, the rest is hand waving. The rest is,
Can I put it back to you though? Because how is it possible to learn from high dimensional data? It's not. It's theoretically impossible
But it works for a reason, and it works because the entire endeavor of machine learning is about essentially finding structure and effectively reducing the dimensionality of data. So why can't a similar approach be applied to natural language understanding?
Okay, but wait. I want to bring up something that Sorcero said, which is, and I think he's right about this, Tim. People often say something like ML works. I think we have to take that with a grain of salt. So it works today because of immense amounts of human engineering that went into creating specific neural network architectures that happen to work. And nobody talks about the 69 different architectures that they tried that failed. They only bring the one that worked, Plan 9, the one that worked. They bring here's the horseshoe network, which is awesome because it's just the first one we thought of. The fact is there was a tremendous amount of human intuition that went into building networks that encode structurally prior knowledge. That's why they work.
Prior knowledge. That's a big part of it, because this pruning of all the massive infinite possibilities where you're playing from data. If you blindly play with data and go up, good luck.
Yeah.
But it's more than what Keith said. It's when we say it's working, where?
Well,
I mean, it's almost working. First of all, let's qualify working. It's almost barely working, and in very tiny. I mean,
it's clearly working in vision. So on very very highly dimensional data sets with tens of thousands of dimensions, it's working brilliantly, right? I agree with you. It's not working at all in language understanding, but that doesn't rule out that some trick might make it work better in the future.
So I disagree with you.
Some similar trick.
Tim, here's my challenge. Yeah. Okay. For somebody to claim that machine learning, pure machine learning without human interference is, quote, working for anything, this is my challenge. You start with a fully connected neural network.
Blank slate.
Fully connected neural network, blank slate. I don't care if you do random initialization. You can do all that crap if you want to. But start with a fully connected network and then train it to do something. Let me see you do that. So you start with a fully connected neural network. I'll even let you tweak, width and height. That's fine. You start with that and show that it can do image recognition, and then I will believe that machine learning works.
Yeah. So no one is disagreeing with you on that, Keith. So the reason it works is we've created inductive priors that essentially the only purpose of these priors is to reduce the dimensionality of the learning.
Circumscribe the problem.
Yeah, exactly.
So then the it and it works. Then this is like one of Walid's binding problems. Is not machine learning. It's human augmented machine learning works.
Oh yeah, but that's a distinction that I thought went without saying. So
okay.
I agree with you.
Okay.
Yep.
Right. But going back to Tim's question, it's not working perfectly in image recognition after all the caveats we said. Second, hold on. I mean, we seem to forget adversarial problems. I can fool a network with 1 pixel. I mean, let's define working. Let's define working, Tim. I mean, and there's a reason for that. It's again the problem of the paradigm itself. I can optimize look, when you optimize going up and with back prop, I can reverse this problem. There's basically there are 3 variables and 1 unknown in the learning process, right? In the learning process, I know the label and I know the object, right? And I'm trying to discover the weights. That's essentially it, right? In adversarial attacks, I know the weights and I know the label. I have to give you X. Again, 3 variables, 2 knowns. I can always do it. In other words, technically speaking, I can always compute a function that produces an output that you think was the result of X, but actually I pushed Z. Adversarial attacks can always happen. Always in this paradigm. Okay? It's simple. I like you optimize in learning. I optimize to find the input that will fool you to produce Y as a label. Done. Okay? The mathematics show that it can always be done. But besides that, I'll say image recognition is a decent application of machine learning. And they did. Okay.
Yeah, on the adversarial examples, I don't see that as being a particularly salient point. I think, given what we know about this spline interpretation of neural networks, it should be obvious that that happens. There may well be similar adversarial attacks on symbolic systems.
Well, there are even
yeah.
adversarial attacks on human beings. I mean, that's the name of the game for
sure.
magic, for illusion artists, right? It's that they create, quote, smoke and mirrors that can fool a person. I think what's interesting about the adversarial examples, though, is that human thought processes, human cognition is fooled in very different ways than machine learning is fooled. Like if you give me a fuzzy hot dog, like even if it's some rainbow matrix that you put on top of it, like I know it's still a hot dog, whereas machine learning, like Walid said, gets tricked by some one little rainbow pixel somewhere that makes it think it. And so, and I think, in my opinion, and look, people have different explanations for what that means, but in my opinion, that hints at people do this kind of higher level, larger scale kind of reasoning, right?
Exactly.
Rather than this very micro detail texture based kind of lookup.
That's right. That's right. Because to say it slightly differently, I agree with you, Keith. This comes down to approximation theory, and neural networks work in the pixel space alone, right? And they learn these polyhedra, and the positioning and pose of these polyhedra is just a function of the training data that they've seen. Human beings perform abstract reasoning. We are traversing concept space, which is an entirely different space.
Yeah, agreed.
But yeah, this is okay. That's another way. Probably it's another way of saying look in a neural network. The information is distributed. There's no structural information. Like nowhere in your neural network are you going to see whiskers of a cat. Okay, so that and it's related to the paradigm itself. And again, we go back to symbolic and structural and discrete information. If we know it's a cat, even though 90% of it is hidden, right? Because I saw whiskers of a cat, right? In a neural network, nowhere you have whiskers of a cat. You have this weird. Actually, if you look deep on the stuff that's inside, nowhere you're going to see anything that on its own will tell you it's a cat. We don't reason like this. We reason it's a cat if it has this and this and this. But without getting too much into...
And for folks that want to do kind of what Walid is talking about, it's the OpenAI microscope, right? That kind of lets you look at saliency maps or visualizations of the different latent layers. Is that right, Tim?
That's it, but I don't think that's helpful in this situation because the OpenAI microscope, that solves an optimization problem to find an input that maximally activates, let's say, a layer in a neural network or a logit or something like that. But what Walid is saying is that when you think about these abstract categories, a logician would go top down. But the way a neural network works, as we just described in our previous episode, is an input example of a cat comes in, and then all the various different features on that will be projected into different parts of the latent space. Right. And then somewhere down the line, there's some kind of softmax, which is saying, are the whiskers there? Is the cat? So it's very bottom up. And there'll be some kind of threshold, right? And then we'll generate the softmax and it will say cat. That's a completely different form of reasoning.
Completely. Actually, it's turned upside down, and then no wonder we have bottom up, top down. It's a top down will say, okay, I wouldn't apply it to image recognition, okay, for many reasons, but I would say if you can find this part and this part, forget everything else. It must be a cat. Like there are salient features that tell me this is a horse. Forget the rest. I don't care. Now, that's a top-down approach. It's a horse if it has this, and it has this if I can find, okay, that's a top. It's difficult to do image recognition top-down. Obviously, we tried for 40 years. It used to be called computer vision. They didn't succeed. It's very difficult. And it turned out that this type of problem, bottom-up, does quite a good job. I mean, with all the limitations we've been discussing, no one came close to. Now some computer vision image recognition systems are mind-boggling. They capture exactly what's happening. Okay, that's good. Language is different. And
well, just with some caveats, I think people don't realize the reason some of these vision models work well is because they are trained to do a very specific task. They're either doing image classification or object detection or segmentation, and they've been trained for a specific number of classes. So they are specifically trained to look for cats. And at some point, if you increase the number of classes that it's looking for, it will get worse, because there's always a trade-off, right? So what happens when you have different types of cats? It's now not going to work very well, is it?
That's why you keep saying it works, but as a practitioner, I have a lot of problems with that, because
it works with so many qualifications, right?
Because when you actually go and try and deploy and use vision models, man, it's a nightmare to actually get them to actually do real world practical problems.
But Keith, it does a lot better than any other paradigm has managed to do. I have to admit. I mean, you try to do symbolic image recognition. Good luck. I mean, it's like, right? So I have to admit that this paradigm,
what are you comparing it to?
This paradigm of going bottom up from raw signals has proved to be more efficient than top-down symbolic approaches.
Exactly. But as long as we caveat, it's a paradigm of trade-offs, engineering trade-offs. Just as Max Welling was saying to us, there's the bias variance trade-off. How much do you leave to the data? How much bias do you put in there? Sometimes having too much bias can hurt you. Sometimes working better in extrapolation makes it work worse for interpolation. The specificity of the task that every single network is trained on, all of these things are engineering trade-offs. Right.
No, I agree. But I have to also give, you just can't refute science. I mean, top-down image recognition in problems where it's essentially pattern recognition problems, top-down discrete methods have failed miserably, right? Okay, so I don't think that's the right paradigm for those, right? So, but the issue is not that to me, still in the big picture of, in the larger scheme of things when we discuss deep learning or machine learning, my issue is not everything is learnable in the first place. So even if you get to the point where you have perfect machine learning machinery, technology, whatever you want to call it, all that's underneath machine learning, even at large, even if that technology becomes perfect, you're never going to learn most of the relevant knowledge that makes us human, because that knowledge is not learnable from data. So I have a bigger question. Regardless of how accurate machine learning or good or bad, all the good, the bad, and the ugly in deep learning, there are most of what matters to us that allows us to function the way we function is not learnable stuff. It's stuff that is either discovered or deduced, or we are told about it by those that discovered it or deduced it. And I can give you an infinite number of examples where to learn that stuff, you would need, and theoretically, that means scientifically and mathematically, you would need an infinite number of examples. Forget it. Okay? But otherwise, if you don't want to do science, then, that's fine. But if you want to do science, an infinite number of examples means no, because we don't have an infinite number of examples. And we don't have an infinite number of years to learn something, okay?
There are folks out there that say it's absolutely fine that neural networks are like hash tables and the human brain is like a hash table. And because what you're saying is that in order to approximate, let's say, some kind of mathematical function, to extrapolate...
I don't want to complicate things, or a common sense fact, like transitivity. People always take me to logic and mathematics. No. It's about a child learning how to walk around. It's much simpler than that. Even those cannot be learned from data.
But we are talking about extrapolation. So you're saying if you have the template and you have the abstract rule, you can extrapolate into any situation. We were talking about this on the show. If you have y equals x squared, you can extrapolate even outside of the training range into any new situation. And you're saying in language, these abstract templates can produce exponentially many data examples. So it doesn't
actually technically speaking, an infinite. Right? But that's
right.
Fine.
So it seems like a pointless thing to say that you could equate understanding to having the magical infinite hash table of the universe, because that doesn't exist. It's a little bit like saying neural networks are Turing complete, or neural networks are universal function approximators. These are appeals to infinity. We don't live in a world where you could have this infinite sampling of reality. We need to have abstract extrapolation.
Exactly. And Tim, we keep forgetting. We don't have, I mean, it's like everything in computation, everything is time and space, storage and time. We also don't have an infinite amount of years. I cannot spend 10 years to learn transitivity and another 25 years to learn the contained in common sense logic template. And so I would have to live 1,000,000 years to know how to walk outside the room. There's also something called effective computability, not just computability. Even if theoretically you can, this is not how we work. Now, people argue, and I say that probably that's the most serious answer I've received, is that, yes, we have built these things using after hundreds of thousands of years of evolution. And they're going to say, we're trying to simulate those years of evolution in machine learning, so give us some time.
Right.
But that's a bogus argument, because when you're talking about things that cannot be learned differently, this is not about evolution. We're not allowed to learn this stuff. Not only we cannot, and we don't have enough time. Learning the ML paradigm that we have now, unless we come up with a different learning paradigm, there are probably, I can envision learning paradigms sometime in the future that are not exactly all bottom up from data. Who says that's the only learning paradigm? But this paradigm, as it exists now, does not explain how in a couple of years a child learns a huge number of high-level templates, pretty much like his neighbor child learned them, although they both have completely different individual experiences.
Yeah, no.
There is no magic here. There's no magic. The contained end relationship, the transitive relationship, blah, 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 these are not subject to individual experiences. This is not something I learn from my sensory input and how I experience the environment and reward. What is the reward in transitivity? There's a lot that we know that has nothing to do with extrapolating from data. End of story. I'm talking about the paradigm at large. Even computationally, whether it's in language or in high-level reasoning. And I'm not talking about formal reasoning, common sense reasoning.
Yeah, and I want to make a comment too on the infinity point that Tim brought up, which is that the infinity that kind of sits in, say, the Turing machine model or any computational model are potential infinities. So the idea is you have an algorithm and it has a potentially infinite tape. Okay, what that means practically is that you can run the algorithm, and if you run out of memory, you save its state. You go and you upgrade your memory, you double your memory, and then you keep computing from then on.
It's
okay,
it's a theoretical infinity.
For a neural network, it's an actual infinity. Like you have to have a circuit,
right,
okay, that's literally already splayed out, actually infinite at training time when you do the training, because it's creating very different, if you want to call it an algorithm, like the calculation that a neural network performs. At the end of the day, every single one of them is equivalent to an unrolled, feed-forward, single-pass network. Right. Okay, no matter how much it's obscured by it's an RNN or an LSTM or whatever, it has this equivalence as this unrolled network. Yeah, and
you mentioned that point with LeCun the other day, and I think he missed the point. The memory in a neural network is different from the memory in a symbolic system. The memory in a symbolic system, I can always increase my memory outside of the logic of the program. I can always add memory.
Yeah, they're not convolved.
The theoretical model is completely different.
That's right.
The memory in a neural network is built in the architecture.
That's right.
You cannot increase the memory without changing your architecture.
Precisely.
In a symbolic system, I can always add more memory and not change a single line of logic.
Yeah, and this has like practical consequences. This has that's a very important point.
That's what computation.
And it has practical consequences, which is that the calculations, the functions that you end up with when you search
the logic,
the space and then NN are very different functions than the functions that we encode as algorithms, as programs. Okay. And this is the crux of why we find that there are very different kind of domains in which these different paradigms perform well, or they perform very differently in different domains. That's the whole point behind pi. I can write a tiny little logic, okay, that can compute pi.
Addition.
Compute the nth digit of pi with an expandable memory, but it will terminate in a finite amount of time, use a finite amount of memory, and give you the answer. There's no finite neural network that you can train that will compute the nth digit of pi.
May I say though, we've discussed this
I know
many times before, and it seems like we're pointing out the obvious.
Right. The whole argument here is that's why some people they keep bringing the point of an exponentially large lookup table. The reason they do that is they have to have this almost infinite neural network to explain things.
Yeah.
So the argument here is not that simple. They know technically that's the only way out, is to have an almost infinite neural network.
I know, but the thing is, infinite neural networks don't exist. As Keith was saying, neural networks have a finite representational power. So I think we should park that. But it's a little bit like talking about, Turing completeness and universal function. It's the road to nowhere from a discussion point of view. So what I want to do is move to a devil's advocate. So if I was a neural network advocate, I would be making a slightly different argument, right? So let's say
God forbid. But
let's say I've been studying computer science, and I've been studying about things like algorithms and dynamic programming and whatnot. And what you're basically saying is that this is a combinatorics problem, right? So what happens if I swap this word in? What happens if I swap that word in? Well, it's like the search space blows up. But if I was a neural network advocate, I would be making the argument, well, when I see that word replaced, why don't I just blow up the search space and then retrain my neural network, just kind of fanning out that part of the search space and do that like lazily evaluated? Why wouldn't I do that?
Where's the data you're going to train on?
No, I would have to I would have some symbolic templates, so it'd be a hybrid model. So I would know that bag is a type of this thing, and then I would blow up some data and retrain myself incrementally.
So you'd have prior knowledge, prior structural knowledge.
Okay, so
Tim,
Tim, so you're going to incorporate a type hierarchy.
You're going to incorporate logic into it.
How else could you do it?
Okay, then
how else would you do it?
Then end of discussion.
No,
then we're done.
So Tim, that's the whole point.
But that would be a useful hybrid, right?
Yeah, but let me take your point seriously. Okay, most likely as a student you would immediately reach towards familiar kind of symbolic logic, programming type tools to augment your. Just a second, let me finish. Augment your neural network, because you realize very quickly, as a human being with your feeble cognition, as feeble as it is, you realize very quickly that just this neural network with data is the road to nowhere. And so you're going to augment it with all the symbolic kind of stuff. Okay, now...
So look, computer science is all about finding the right abstraction. That's what, the guy who invented C++, he said that on the Lex Friedman show. Right? You find the right abstraction.
Okay, but here's the problem. Okay, and I agree with you. Like, that's the way a practical person would do it. Here's the problem, is that that's still limited by human beings' capability to perform that, intuitive, logical, symbolic, kind of reasoning to come up with the abstractions, etc. And the holy grail is, can we get a machine to do that? Like, we really want a machine to go out. Well, hold on. We really would love it if we could just, I don't know, feed a bunch of, metrics from the solar system and experiments on Earth and Michelson-Morley and whatever else, and have it go, aha, I have discovered general relativity for you. Here's the set of symbolic equations that describe, the system you've given me. Like, that's what we want to be able to do. The problem is neural networks are not going to get us there. Okay, they're just the current paradigm of neural networks are not going to get us there, and we really would like people to take that fact seriously, to devote more effort into whatever that future system is. Hybrid systems, neural networks with symbolic layers integrated. I don't know. Differentiable neural computers. Who knows?
I have another twist on Tim's suggestion. If you're going to augment a neural network with these symbolic structures, so obviously one of them is going to be a type hierarchy where a briefcase and a suitcase and a bag, they're all containers of sorts. You have to have that, right? Otherwise, we're back to the combinatorics. Okay. And you're going to have a laptop and a ball and a trophy or like artifacts, blah, blah, blah. Right? And you're going to have a rule like we started with. If X is bigger than Y, then X will not fit in Y, blah, blah, blah. Okay. So basically, then you're using a neural network. I'm assuming still you insist on using it since all of that knowledge now is already structured. You're using a neural net, I'm assuming, for its learning capability.
Well, either
right?
It's learning or its compositional ability.
We can put the second one into a discussion because I'm not sure what you mean exactly by that. But
well, just for example, you don't need to write a parser. You don't need to know really anything at all. You can just load a sentence into a vector, and you can.
You still do because you want to know what augments what and what goes where. You still do, but let's not get into the technical details. To me, and I think you both agree, the strongest point of neural networks is the learnability. As a matter of fact, if that wasn't the thing that is different from symbolic systems, it would never have come to this place.
Differentiable
learnability is the that is the.
But that's partly my point. You don't need to know any technical knowledge about language. All you need to do is train a transformer model on some data from Wikipedia, and it will just magically represent it in a vector space.
You're saying, then I misunderstood you. You're saying your training data is expanded massively using the type hierarchy. And so basically you're creating, instead of a single example, you're blowing it up into 200 million examples by instantiating it with different...
But doing it lazily. So when you see something come up, it's a little bit like search engines. They take words and they do query expansions.
So the augmentation is on the data. You're simulating an infinite number of examples a child might see in your data, and then
not a priori on demand. So when a query comes in,
that's a technical detail.
I can take some words. I can use but the question then is: should the type hierarchy be human designed, or could we search for it?
The human hierarchy is not an issue because I don't want to get into the ontology, because in my mind, the nature of things is well defined, and it's not up to us. And a tree is a tree, and a tree is a living thing. And unless someone, a real ontology that's underneath language, if anyone questions it, we have a label for them. We say they're mentally challenged, right? If someone says a tree is not a living thing, you could always say that. But let's put the ontological categories, not everything in nature, but the basic ontological categories that a child is aware of when they're 3 or 4. I'm still baffled by, if the learnability is the biggest thing, right? Then why a neural network? I can do inductive logic programming, which learns from these templates and actually learns very effectively. Then why a neural network? What I'm baffled by is, it fails to do this and it fails to do that, but let's keep the neural network. What is it? What is it that is, is it just because we have neurons in the brain and we think somehow by calling something neural, we're going to find something magical? I am really baffled. Inductive logic programming is so powerful if it was given enough genetic algorithms can learn. Why is it we insist that Let's do all these fixes outside and keep the neural network.
I think it's brittleness. That should be clear. So the knowledge acquisition bottleneck and the brittleness of the knowledge representation, meaning that every system that got designed, all of the common sense knowledge would have to be recaptured again from scratch. That's the only reason why neural networks are being used today. It's the ability for you to train a neural network once and use it in a variety of downstream applications.
But we just agreed that it was not on its own. It doesn't
work very well.
No,
well, it wasn't even trained once.
It
was trained on demand by a symbolic data generation process, right?
So we're back to square one.
Sure. But one thing that we were saying just before the conversation started was we are now seeing folks use hybrid systems to extend these models, right? Like DeepMind, they've done this information retrieval system where you put a query in and it will go to Google a bunch of times and it will stitch this prompt together and then stick it into GPT-3. So, Walid, you thought that was actually almost them admitting defeat to a certain extent.
Oh yeah, they were saying that we can't keep increasing this indefinitely. I mean, even if I have trillions of parameters, actually they showed that the improvement in performance was negligible. I
mean, can you link that? Can you link that article for me? I'm going to take a look at that.
Yeah, there's a couple of things. Actually, they're on the DeepMind site. I think one of them. Basically, they proved and they stated explicitly that whether it's trillions or 1 billion, it's almost the same. And so anyway, some of us knew that, but hey, now it's proven by machine learning people themselves. But they're actually now saying we need an infinite amount of data. I kept talking about infinity, that these guys are trying to chase infinity, and now they are admitting in a paper, yes, it looks like we have to chase infinity. Like, how much data do you need?
It's like the category theory, folks. It's like you have, arrows pointing to other arrows, pointing to groups of arrows. Yeah. Well, hey, if we just go to infinity, then we'll have to not worry about this increasing hierarchy anymore.
Yeah, I get the feeling category theory is also too abstract to be.
There's a big difference between a potential infinity and an actual infinity. It's like if I'm trying to play the latest version of, Quake or Doom or whatever's the latest, greatest from ID, and my computer doesn't have enough memory and it's kind of choppy, it's really easy for me to go get another memory stick and plug it in. I don't have to recode the software, like, to take advantage of that. I don't have to retrain the game, like, in order to play.
Actually, infinity is really at the heart of this. Remember the paper that actually proved on the side, it proved the equivalence between compression and learnability. But the point of the paper was they used Cantor's results and Gödel's results that basically infinities are not all equal. The argument in set theory that, okay, the set of integers is infinite, the set of reals is infinite, but obviously one infinity is larger than another infinity.
Aleph 0, Aleph 1, etc.
Aleph 1, so there are infinities, and Gödel tried to see if you can prove, because this is not proven, believe it or not, that there are infinities that are different in size. And Gödel proved that you cannot prove this. It's an open question, but intuitively, it makes sense that the real infinite is bigger than the integer infinite. But besides that point, those guys used this result to prove that learnability can be undecidable. Now, here's what the real result is. In doing that, they prove compressibility and learnability are equivalent, but I quote that for other reasons, for language. But there's a bigger result, or there's a more important implication in the result. Basically, there are tractable infinities and intractable infinities. Language is an infinite thing, but it's very tractable. I don't know what makes it, and I'm looking into that now. I don't know what makes, but it's related to top down and bottom up. So, for example, in doing image recognition by a symbolic approach, discrete approach, you're going into an intractable infinity. The number of features and rules you would have to put is probably intractable. Bottom up here, you're also playing with infinity, but it's a tractable infinity. There are problems the other way around. So let's take...
I want to define tractable.
Tractable is because you can deal with infinite domains and get a result. I mean, we do it all the time.
Right.
Any mathematical function is infinite. It's an infinite hash table.
You just said a second ago that vision was different to language because it was intractable. So exactly how is vision different to language?
I'm thinking out loud now as we speak. This is the latest thing that is on my mind. And it's related to top-down problem solving versus bottom-up. There are problems that they are naturally solvable bottom-up. Image recognition is one of them. If you take things like discovering a sorting algorithm, it just cannot happen bottom-up, because let's imagine I didn't know of quick sort or merge sort. I didn't know of it. We're still in the 40s, right? And I want to come up with it. Let's think about it bottom-up. How would you start? Saying, if you try this with this, and if you try this with it, you're dealing with infinite, and I'll show you top-down you're dealing with infinite, but it's a tractable infinite. It is naturally a top-down kind of problem. Bottom-up, you will never assemble things in certain ways that will allow you to come up with merge sort. Forget it. Top-down, it's easy. Okay, if I replace this by this, let's try this. Replace this statement with an equivalent statement. So top-down, I can deduce a new sorting algorithm. What I'm saying is there are problems that are naturally solvable top-down more than others. And we've learned that in at least in problem-solving courses, logic. And there are problems, on the other hand, that are more naturally solvable bottom-up. In both cases, you're in an infinite domain. But to reach a tractable solution in that infinite domain, bottom-up is better than top-down.
Let's linger on top-down for a second, because this is very similar to the work from Josh Tannenbaum doing the inductive program search. Yeah. So that is also an exponential problem, because we're always dealing with exponential blow-ups, whether it's the curse of dimensionality, whether it's the templates, whether it's the combinatorics of the search space. So if you go top-down, you have a combinatorial problem, right? But I know that Josh Tannenbaum has, I think with Dreamcoder, discovered sorting algorithms, presumably ones which are similar to quicksort. So what's the problem here? Is it because there's a verification problem, and after it discovered it, you wouldn't be able to reason about its behavior? What's the limiting factor here?
So I'll tell you about sorting, for example. In top-down approaches require symbolic knowledge. So if I'm going from, I can show you how you, from insertion sort, which is the most intuitive way of sorting, right? Basically, you're saying, if I have more than one object, assume the rest is sorted, then all I have to do is insert this in the right place and the whole thing will be sorted. So the most intuitive way of sorting is insertion sort. I can show you, starting from insertion sort and going through some transformations, which could be infinite because you can always come back and go, right? It's an infinite space of possibilities. Where can I go from a certain function by doing semantically preserving transformations, let's call them. I can show you with 4 or 5 transformations, you get merge sort, which is the optimal sorting from the most inefficient. Okay, this can be easily done top-down because I'm using symbolic logic. I'm using symbolic knowledge that this statement is equivalent to this, that I can replace this by this. So, for example, I can replace X attached to a list by X in a list appended to that list. They're equivalent. So I can use basically equivalences. I can use arithmetic transformations that I know they're meaning preserving. Long story short, top down with few transformations, because I'm guided by where I'm going in my search space. I know where I'm going, and I can do this. Bottom up, you know what you would have to do in this problem? You would have to patch together every combination of things that you can have to come up with something. It's almost, it probably can be done, but it probably would need, I can't even imagine how many steps it will take to come up with something that bottom up theorem. If I start with a working program and all I did are meaning preserving transformations, then whatever I get is a working program. Okay, so let's put that. I don't need to execute it, but how do I know it's an optimal one? Or how do I know that's a different problem? How do I know it has better complexity?
When you say meaning preserving, do you mean it does the same thing?
It's about semantics. A program semantically is a hash table. Input, output. It's an infinite hash table. Any list you give me, the output is a sorted list. In this case, right? Okay, so any program, the semantics of any program is an infinite hash table from input to output. By the way, this is basic computation. Any program on Earth is an infinite hash table. For these inputs, I give you these outputs, and it never ends for all. For all X, Y, Z, I give you R. Right? Okay. Meaning preserving means these two programs, no matter how you write them, will produce the same table, extension. Their intention is different. Extension, what they produce, is the same.
But quicksort might have a different intention.
Yes, intention. I don't care. My whole point is to do intentional transformations. To get at another property of the program, right? Which is its time complexity. Probably I don't care about the space complexity. But one property of the program, as we know, is the extension, the function. I have to preserve the function because my end goal is to have the same semantic function in the end, right?
Sure.
And I want to play with the intention to produce another program that gives me a better attribute somewhere else, which is time complexity.
Sure, but isn't there uncountably infinite many intentions that could produce an n log n time complexity?
Right. You can always say, I have a better complexity analytically, that this performance is better than this. I know that. Did I reach the optimal? That's an open question. We don't know if we can beat n log n.
You know, you can statistically measure time complexity by running the algorithm. So like you did on one input. So you give it an input, you see how many cycles it takes.
Yes, crudely, yes. And they do this in numerical analysis.
Yeah. So you can get an approximation for its time. We do that kind of thing all the time. Actually, like that's a pretty common, computer science activity if you can't prove it. And then there are cases where algorithms, or where problems have theoretically proven, upper and lower bounds on complexity. Like you can't possibly do better than this complexity.
Better than that. Right.
And, and if you're doing any worse than this one, you're like,
If you add parallel programming into the picture, analyzing, like search becomes constant. Like if I have a list of 100 elements and I have 100 processes, it's log n.
Well,
it can't be constant because you have to wait for all the results and combine them at some point.
And that's a whole area of study as well, is like how parallelizable are problems, what the speed
there's
up
a limit
is,
to parallelization,
etc. So I did just want to say, there are practical means in this. Number one, it's task specific. Like we keep running into this over and over again, which is that some tasks are, have provable aspects, some don't. You can do empirical measurements. But if you're talking about the general problem, like just the general problem of give me, so like Chalet's kind of conception of things, like I have this general intelligence, which you give it a task and kind of an oracle, and then it derives algorithms, to solve that particular task. That's the general AI. For that general task, I think this is a lot of what Walid is talking about, which is kind of these general limitations on like an algorithm that finds algorithms, or things like that. And that's where, and that's obviously what we want some general AI to do. So like kind of you mentioned Dreamcoder, exactly what the Dreamcoder kind of abstract talks about, right? Which is, look, the ideal is that we have programs that write other programs, and they do so in a way that's kind of modular, and they reuse components, and therefore they're much more efficient than just exploring this combinatorial space of like all possible programs. And just one really quick point here, just for our listeners, I want to point out a couple things, which is one, the space of all computer programs is countably infinite. And in fact, that was important in, Gödel's proof of incompleteness, because he developed this mapping between, the real or natural numbers and computer programs, and was able to show that there are statements that are true that, can't be proven. And then I wanted to come back to one thing, Walid, which is, what were you saying was still an open question in terms of sort of sizes of infinity? Because the only one I'm aware of right now is just that, if you have Aleph 0, which is like the infinity of natural numbers, and Aleph 1, which is the infinity of the power set of natural numbers. So it's like the next most provably larger, class of infinity. There's an open question as to whether there's anything in between. And so, like, the famous one is the continuum hypothesis, which says that the complexity
this is what I was trying to recall. Okay. The continuum hypothesis, which Gödel said will never be. We will never know if it's true or false. It's a hypothesis.
In other words, Gödel is saying that the continuum hypothesis is itself a Gödel statement.
It is an unprovable statement either way. And they use that to say this translates to, in machine learning, to some problems that will hit the false, because the continuum hypothesis could be true or false.
Mm-hmm.
And they proved in that paper that there are some machine learning problems. There are some problems where machine learning is intractable for, while some, it's quite good, which sort of summarizes what we've been talking about. Like, what is learnable, first of all, and what is effectively learnable? And so their proof was, hey, machine learning is not the end of all, and it's not the only game in town. There are problems where machine learning is not the right tool. The reason I bring that
Sacrilege.
up is...
Can't believe you said that, Wally. You're going to be burned at this stage.
Okay. I'm going to... Well, I'm now living in D.C. The Bay Area was a dangerous place to say that.
D.C. is safer, huh? Okay.
Safer. Let's put it that way. Moderately. And so that's what brought us to, take something like sorting and improving a bad sorting algorithm into... That's a top-down problem, and it's manageable because I know how to do meaning-preserving transformations top-down. I have the rules, but that requires symbolic manipulation. There's no other way. Doing it bottom-up, I can't even begin to start thinking how you would do that. And I can imagine many other problems like that. On the other hand, I mentioned that pattern recognition types of problems, like image recognition, I can't even start thinking how you would do it top-down symbolically. So that paper, it opened my eyes like, wait a minute, there is a good, it's like there's a good infinity and a bad infinity. And and it's related to top down versus bottom up.
Just because you can't think about how you could do image recognition top down doesn't necessarily mean that you can't do it.
Yeah, of course not.
Of course. I don't send 10 commandments here. No, I'm just saying I can't.
I'm interested in this continuum of human design because, Walid, you're a huge advocate of humans being able to design knowledge and AI architectures, right? I have a suspicion that a working AGI architecture might be an emergent property of some low-level system, or it might be something which is just beyond our comprehension.
I agree with you that there's going to be an emergent. If you don't have AGI if you cannot somehow simulate emergence. Definitely. But from zero, no. From blank slate, no. Look, everything, even geometry, has to sit on some axioms. I mean, call them the axioms of nature. I don't know. But there's no way we're starting blank because the degrees of freedom are, where do you go? You have to have some axioms. They call them in some AI corners, they call them common sense naive physics. They call them common sense psychology. They call them, it's the common sense of how the world functions at a pretty basic level. You have to start from somewhere. So that's my only...
You do. But it's quite interesting that in the machine learning world, the reason it works is maybe the physical rules that govern our universe only produce very few factors of variation, which means the curse of dimensionality might not be such a huge big deal. And I think similarly, you could apply the same rationale to certain types of abstract category and certain types of, mathematics, for example. In some sense, it's actually much simpler than we realize, which means any AGI emergent property could have emerged from few abstract categories, not the uncountably many that we suspect.
Right. Two things on that. It's a good point. The uncountably, the few could be a lot more than you might think. What you're saying, we're going to end up with a few. That few is a huge few. Okay, that's one point, which is unmanageable. I mean, I can think of problems. We just talked about sort. Imagine starting bottom up from that few is not that innocent like few would entail. There are some combinations that we don't look at all because they're not part of the nature. These combinations just don't exist. So the only combinations that can make sense are the ones that we're going to look at. This is in the physical world, it's true, but in the abstract world, I can imagine unthinkable concepts that can't physically happen.
But it's not about what you can imagine, it's about the intrinsic complexity or structure. So I'm making the case that physical reality is actually much simpler than we realize. It's generated by simple physical rules, and also the same thing works in concept space. I'm making the argument that if you abstract enough, there are very few, relatively speaking, abstract templates that we need to describe the world that we live in, like the transitive template.
Right. Okay, that's a nice project. What are, just to size it up, like are we talking the order of 1 million, 10 million, 100 million? That's a good point. What are these abstract templates out of which we instantiate everything we see and we observe? Interesting question. I don't know.
Everything that we experience in our physical reality should be describable by abstract templates, which could extrapolate into any situation and experience space.
Which I believe by the way.
I know. Yeah, and then,
but that includes events. Now imagine. I mean, the other day I was going back to dig into the semantics of events. Events have their own logic, and events contain other events. So a big event contains sub-events, and events might overlap, and one might precede the other exactly. I mean, there's a whole logic for events. And it's a clear logic that cannot be disputed. It's not up to us, right? Events have a starting point and an end point. They have a duration. So there's a neat logic for, it's called the logic of events. I don't know how many templates you can generate there, and we take them for granted. We function in the world based on them. We don't know we're following these templates of event logic. I mean, there's a logic behind events. When you are told this thing is happening now, you can immediately trigger so many templates that you know. So I don't know, it's a big question. How many of those we have? I have no idea. It's
and you're saying that that's just the logic of the universe. So in the universe, there is a logic of events, and we acquired that logic.
And at least in the universe we live in, it seems like you can't beat any of these templates. You can't refute it. And there's no way this can be grasped from experience. I mean, it's beyond us to say that. I mean, if you look at the logic of events, the reason I mention that is I'm always mentioning transitivity because it's something simple people relate to. But there are many others. It's called naive physics, how the world works. I mean, it's at least the universe we're aware of, and you can't beat them. You can't beat any of these rules. It's not up to us. That's how the world functions. Actually, which brings me to another point. We give ourselves too much credit. Humans, we think we're inventing. We invent very little. We are barely discovering what's out there. So we give, we think the world will not run without us. It's the other way around. The world runs in spite of us. We're just trying to discover. We're just trying to discover those metaphysical realities that most of them are not learned. They are there, and we stumble upon them and we discover them.
So hang on, are you saying the logic of events is a bit like a meme? And it's not that somehow I acquire it. I wasn't born with it, because it's a meme that floats around, and then I'm through instruction, I'm taught how the logic of events works.
I believe more than that. I believe these templates are part of our genetic. and how they got imprinted and when did we acquire them? Big question. I have no idea. But I think they're instantiated, and immediately we pick them up. We say, this is that. That's it. All I need to do is see one example, and all of a sudden that template becomes instantiated. It's like initially it was like wrapped in a box, never used, and when I see one example of it, now it becomes active, and I have proof that it works. I saw actually an instance where it was instantiated perfectly and it works. So now it becomes not just a nice wrapped template that I never used. I've used it, and I know it. And most of these, don't ask me how many are there, are like that, because I can't think of any other plausible explanation. I mean, to tell me that I've seen a couple of events and they work this way. First of all, there's so many. And second of all, I and you cannot see them differently. These templates work. They work in spite of us. Like Plato said, they work even if the universe didn't exist.
Well, hold on a minute, to just before we get to that point, because that muddies the waters a little bit. But you're saying that all of these templates, like the logic of events, they are a projection of physical reality, and then we essentially kind of inherit them eventually in our DNA code. And the efficiency of information transfer between physical reality and our DNA code is something that we can be discussed. So as you just said, we haven't discovered all of the templates yet. There are still many more projected by physical reality that we haven't discovered yet.
Because we never had the opportunity to instantiate them. So there might be so many still wrapped up, never used.
Yes, but this gets to the main point, which is that the templates are an emergent phenomenon of physical reality. So you could try and model the templates, or you could go a level deeper and try and recreate this physical system where the templates are an emergent property. Wouldn't it be better to do that?
Okay. So this is like, where did these templates come from, basically? It's in a sense, that's what you're asking.
They must be an emergent property of our physical reality.
It's one for all. Like, this did not happen individually. It could be it happened for a template human, and we've inherited all of us the same templates. The reason I say that, we're not allowed to have them differently. This is a key point. And instance-based learning is a completely opposite paradigm. It's based on what I see and what I observe. These templates are not susceptible to this weakness. So they could have been. Here's the thing. There was a template human, an abstract Platonic human, that learned these templates, and then we all inherited them. Done. We're going really deep sci-fi here, but the reason I'm saying that is we're not allowed to learn them individually.
You were going to make the assertion that the templates would exist even if the universe didn't exist, and I don't agree with that. I think the templates are an emergent property of the universe.
Do you think transitivity gives a damn if planet Earth did not exist?
Well, you've got me on that one, but the logic of events certainly wouldn't exist if the universe didn't exist.
We can quibble on which ones can live in the ether and in the universe at large, but my point is there's a huge number of these that we're not allowed to learn them differently, and we don't have time to learn them. Mm-hmm. We just don't have time. So they are there somewhere. Where did they come from? How did we all acknowledge them willingly or unwillingly? We have no choice. I mean, if we just took them and we function based on them without even knowing.
I agree. And if there was another civilization on another planet, they would also acquire the knowledge of events.
Right.
That seems fairly obvious to me.
Yeah, I can't see transitivity not being true on any planet, right, or any galaxy, right?
The real problem from our point of view is we want to create artificial general intelligence. Right. And actually the problem is one of representational primitives. You believe that we should design the abstract categories to resemble the emergent categories the universe gives us.
Right. Or
even
at
though there
least,
are almost uncountably many of them, you think?
but there could be some that are a composition of others. So
Right.
we need to do at least the most basic primitive ones. I made a reference in the latest article I posted on my blog to Gordon and Hobbes' book on common sense psychology. And they go through a lot of these, and they're coded actually in Lisp. But so we have to code these basic, I don't know, there could be 10,000 of them. But each one of them is very simple, and the logic of it is quite simple. An intelligent machine has to know these things. You can't function. I mean, you can't have an autonomous car that doesn't know the basic logic of contained in. And there are so many of these that a 3-year-old functions based on them without knowing. You tell a little kid, can you please put the laptop in my briefcase? Oh, Dad, it doesn't fit. Try to tell them to put it in a smaller one. They say, what? You're toying with me? Right. So a 3-year-old knows that doesn't fit is transitive, or bigger than, or smaller than, inversely.
Mm-hmm.
And they function based on, and we function every day based on a lot of these templates, whether it's the logic of events, the logic of physical size and I cannot imagine learning these from scratches. What do you mean it's all from data? No, these high-level templates, we are respecting how the universe works. We give each other too much credit. It's not all up to us. Very little is up to us.
Jan LeCun says that deep learning models can perform discrete reasoning. And I just want to pick this apart because I think what they mean is they have this hash table or storage view of neural networks. And what you're talking about, the kind of reasoning you're talking about, doesn't require any storage, right? All you need is a function that takes an input and it gives you an output that could extrapolate anywhere in experience space, right?
Right. And
that's the difference.
We know that's the huge difference. We conquered infinity with that difference. Look, I mean, I might store a few things just out of laziness. Sometimes we store them, like, for example, I have a few things that I don't compute now. Like I recall them from my, I don't know why I store these, because maybe they're most frequently asked of me. So I store them because I want to be lazy here, not to recompute them. But to store everything, this is ridiculous. I mean, we recompute, but there's an implication by we compute, not store most of the stuff. The big implication is a killer for the ML paradigm, at least the current model. The first killer is I have to have symbols.
Yeah.
There is no other way I can compute stuff and not store them without symbols. Second, there's a quantification and there's a symbolic representation. It's not just a calculation, it's symbolic. I have symbolic storage of intentional objects, infinite objects, like addition. I have an algorithm and stored.
Yeah.
Not just a symbol and some string in a table. The implication is huge. That means I have functions, procedures, intentional descriptions, finite descriptions of infinite objects. What does it mean to have multiplication in my head? That means I have an infinite hash table of multiplication in my mind that I can always produce.
Yeah. I know, but I think this is even simpler than most people realize. It just comes down to this computer science trade-off of compute versus storage. As an engineer, I see it all the time. Sometimes it's cheaper for me to cache some computation and stick it in a hash table and pull it on demand. And sometimes it's better for lazy evaluation to compute something. Now that we know how neural networks work, they are hash tables. An input, because I think the problem is people think of neural networks as having some kind of computation. There's no computation.
Look, the reason for that, it took me a while actually, because the initial paradigm conveys function computation, because a neural network in the end is a composition of many Fs at every layer. I mean, you think of a neural network as F1 of F2 of F3, where every F is computing each layer, and the input of this layer is now. So it is thought of as function composition. And that immediately gives you the impression that, function composition, that's a computation, that's a program. Well, yes and no, because the algorithm and the intelligence is in the data itself. So in other words, it's different from symbolic computation. You're storing the logic and what the data told you in your architecture.
Yeah, people think of it as a function composition, but it's
Right.
actually not. We used to think that it was performing successive functions. Actually, every single input that goes into a neural network is definable with a single affine transformation.
Right.
Yeah.
Because in the end, function composition is a function. Look,
Exactly.
yeah. But you know what the functions are doing at every layer? They're building the keys in this hash table.
Yes.
That's
Exactly.
all they're doing.
Exactly.
It's a big hashing function.
Yeah.
And then your weights are the lookup. So basically, what you're doing is all these function compositions are building a very sophisticated hash key.
Yeah, it's all the keys. Every single neuron in a neural network is a hyperplane, which might be the face of the polyhedra that input example goes into. So every single neuron is a key.
Is a key.
And
well, the key there's a composite key. So a certain input might have these neurons, right? I mean that's what the softmax in the end figures out, that okay, this object has these neurons contributing to its key. So you're a dog. Okay, so I looked you up, I fetched you, and there are some neurons that are going to determine what you are. So I looked you up. It's an unbelievable way of making very smart, fuzzy, and the keys are fuzzy, by the way.
It comes into a trade-off between approximation, statistical, and optimization complexity versus computation complexity. Because if you think about it,
and limited storage.
That's right. So what you're doing is you're tessellating this Euclidean space, and it's an exponentially large. It's very, very large, but the reality that we live in is infinitely large. So infinitely large is significantly bigger than exponential Euclidean space, right? There's no comparison.
Right, no comparison. And when you add the very sophisticated way of making lookup keys, there's even more magic happening than this is it. This is why it's such a powerful device. And I'm not minimizing it.
Yeah.
But let's be safe. Let's not say this. That's the only issue. I mean, but it's a brilliant way of reducing my initial lookup is infinite, like you said. It's then exponential, but with enough training and enough layers, especially the deepness, I am making a very sophisticated key where I can now look you up with high certainty of accuracy.
Mm-hmm.
It's amazing if you look at it. But to take that and say AGI, transferability, which is a huge thing that's being ignored in the community. You know why? We were just talking when Keith was here about the architecture and the algorithm are intertwined, and the memory, right? So transferability is almost impossible. Like you cannot, because it's like you're saying, I wrote an algorithm that will do everything. If you equate the algorithm, like what? No, there's in symbolic computation, I have an algorithm that does this. In a neural network, the architecture is your algorithm. So transfer what? I mean, what are you talking about? You have a universal program that solves everything? You can't. The mathematician in Keith got it. If I have an infinite neural network, yes, because I can inhibit certain part of the network for one algorithm, and then so it's like I have all the algorithms in one infinite neural network. But that's insane. Right?
Yeah, exactly. The interesting thing is that neural networks work at all, because there is an infinite experience space, combinatorially large, but there's a lot of structure there.
Here I have to give, I mean, really, if anything, Jeff Hinton's Turing Award is probably worthy. The backpropagation algorithm was a huge invention. I mean, to optimize, well, there's the limitation of differentiability, but that aside, it's a genius. I mean, we're talking about building these keys to do lookup on unseen data. That's the magic. So it is because that's where the magic happens. That's where you keep adjusting these weights. Basically, you're improving on your keys, on your lookup function. Or if you want to think about it, but it's genius. If you think about but it has its limitation. It's a powerful machine.
Backpropagation is all about how do you move these basis functions, these hyperplanes. They're quite uniformly spaced out in the input space. So what backpropagation actually does is it changes all of the poses to chop up the input space around your training data.
Chopping up is the key here.
It's the key. So that chops up the input space, but that's on MLPs, and that doesn't get you very far. The deep learning revolution has little to do with backpropagation. It has a lot to do with convolutional neural networks. It has a lot to do with the ReLU function. It has a lot to do with all the cloud computing revolution. Data sets.
Activation.
Yeah.
Well, the cloud computing is performance and scaling. I mean, okay, I'm talking about. Right, but I'm talking about expressive power as a paradigm. I mean, yes, activation functions. There was a lot of advances in like ReLU and all the new methods of. It's sort of similar to our computers are still von Neumann machines, but they're nowhere near what the initial von Neumann machine was. But in terms of it's not expressive power. In terms of what it can do, we're still in the same Venn diagram, in the same space.
Yeah.
The technology improved, not the science. I mean, not the, if you want to compare them, but essentially it's the same paradigm, which was genius, still is. It has its place. My only issue is when people start saying, this universal quantification, it will do everything. I don't need symbolic. I mean, it's just because I'm stuck with this architecture that is data-driven. And when you talk about self-supervision, like, what exactly do you mean? Again, we're back to blank slate learning from, and that's too extreme. And I can't see in many problems, not just language and common sense, in many problems, even, like I said, naive physics. So, but the debate is fun. The debate itself is fun because I hope we learn from each other, but it's fun always. Thank you.